Hello everyone, I'm Ahmet Yükseltürk and I'm going to present the paper titled Recollection Center Location for End-of-Life Electric Vehicle Batteries Using Fleet Size Forecast Scenario Analysis for Germany. This is a joint work with Aleksandra Wewer, Pinar Bilge and Franz Dietrich, all from TU Berlin. Here is the structure of the presentation. I will make an introduction and briefly discuss related works from the literature. I will continue with problem definition and the description of the mathematical model. Then I will share the results of our case study and conclude my talk. Let's start with some statistics. According to International Energy Agency, in 2019, the global electric vehicle fleet size was 7.2 million, and in 2030, it's expected to reach 140 million. One of the critical parts of electric vehicles is the battery. In the near future, first generation of electric vehicles will reach their end of life. So in order to prevent formation of battery landfills, we must make vehicle batteries part of a circular economy value chain. Preliminary observations show that batteries still retain up to 80% of their capacity after 8 to 10 years of driving, so repurposing of batteries before recycling is a possible life cycle scenario. As an initial step, batteries should be recollected. In this paper, we focus on the location decision of recollection centers for end-of-life electric vehicle batteries. Now I will discuss related works from the literature. Possible repurposing applications of electric vehicle batteries are peak time energy shifting at homes or energy leveling of renewable energy sources. In these settings, the battery is charged during low demand periods and discharged when the energy demand increases. In the figure, you see repurposed vehicle batteries used in an energy storage system on an industrial site in Belgium. Note that batteries should be reprocessed in order to complete condition monitoring, repair and maintenance operations. We expect that the repurposing will be done in a specialized facility. Since currently the batteries are not standardized and vehicles have different battery types, these facilities should adopt principles of flexible mass customization. In our paper, we use the facility location model. In these models, there are regions served by facilities, and we want to find the location of facilities so that a predefined objective function is minimized. Since every application has its own set of constraints, models should be adapted for each setting. In the literature, there are two works related with facility location for end-of-life vehicle batteries. First one is by Tadaros. In this work, the facilities are inspection and recycling centers, and the region is Sweden. The objective is to minimize the total cost of operation. The second work is by Satre et al. In this work, the facilities are second life locations of batteries and a recycling center. The region is state of California in United States of America. The objective is to minimize the total weighted distance. Note that in the first work by Tadaros, the fleet size distribution is assumed to be constant through time. Since electric vehicles are new products, we expect that distribution of vehicles will change through time. In the second work by Satre et al., the fleet size distribution is dynamic. However, only one recycling center is located. Therefore, we conclude that there is a need to develop a model where the fleet size distribution is dynamic and more than one facility is located. Now I will define the problem. We have regions with electric vehicles. We assume that batteries that reach their end of life will be brought to a collection point near to the owner's residence. Then, batteries will be transported from a collection point to a recollection center. Since batteries are hazardous materials and there is a risk of fire during the transportation, we impose an upper bound on travel duration from collection points to a recollection center. And our objective is to locate recollection centers such that the total transportation time of all batteries is minimized. Now I will present the mathematical model. We have three sets: population regions, possible locations of recollection centers, and time periods. We have two types of parameters. First one is the battery inventory, and the second one is travel duration between regions and recollection centers. We have two types of decision variables and one objective function. We minimize the total transportation time of all batteries from regions to recollection centers. And we have the following constraints. If a recollection center is not operational in a location, we cannot assign a region to that location. Since recollection centers are specialized facilities and need high investment, once we open a recollection center, it continues to operate until the end of time periods. In each time period, each region is assigned only to one recollection center. However, the assignment may change through time periods. We specify the total number of recollection centers for each time period, and finally, we impose an upper bound on the travel duration. Now, I will share the results of our case study. We solved our model using data from Germany. According to Kraftfahrtbundesamt, in English Federal Motor Transport Authority, a German official institution, there are 400 districts in Germany. Our time period is from 2030 to 2060. We locate three recollection centers in one of these 400 districts, first one in 2030 and a new one every other decade. Since hybrid and electric vehicles have a battery, we use statistics for both of these vehicle types and we refer to them as e-vehicles. We assume a constant battery lifetime of 10 years. That means battery of an e-vehicle registered this year will be available for repurposing after 10 years. The upper bound on travel duration is 6 hours. We selected this value because a lower upper bound makes the model infeasible. 6 hours is also in line with hours of service regulations of Germany. We obtain travel duration information between 400 districts from open route service. Now I will talk about calculation of battery inventories in each district. We have three steps. In the first step, we determine new vehicle registrations. In the second step, we determine how many of these new registrations are e-vehicles. In the third step, we distribute e-vehicles to districts. The annual rate of change of new registrations in Germany between 2009 and 2019 is minus 0.1%. So we assume that new registration numbers will not change and will be equal to 2019 registration levels. So approximately 3.6 million vehicles will be registered each year. Now we need to calculate number of e-vehicles. We use three different penetration scenarios: normal, optimistic, and pessimistic. In the normal scenario, in 2050, 90% of new registrations will be e-vehicles. This represents Green New Deal plan of European Union. In the optimistic scenario, we reach 90% penetration level in 2030. In the pessimistic scenario, we have a lower final penetration ratio. For each scenario, we calculate the number of total e-vehicles for each time period. In the third step, we distribute e-vehicles to districts. Note that fleet size distribution is dynamic through time. First, let's see a small example. Suppose we have only two districts, A and B, and in the initial time period, half of vehicles are in district A and the other half in district B. Now, if we look at the distribution of e-vehicles in the initial time period, we see that 3/4 of e-vehicles are in district A and 1/4 in district B. We assume that as we proceed in time, share of new e-vehicles registered in district A will change linearly, and at the final time period, it will be equal to the share of all vehicles in initial period. That is, in the final time period, 1/2 of new e-vehicles will be in district A and the other half in district B, because this was the initial vehicle distribution between districts. In the table, you see data from three districts in Germany. District 1 has 4.83% of all e-vehicles in Germany, However, only 2.57% of all vehicles are in that district. So, the share of new A vehicles that go to District 1 will decrease through time. The share of District 2 has an increasing trend, and the share of District 3 remains constant. We solved the model using Gurobi. The results for all three scenarios are same. First center is opened in middle western part of Germany, the second one in the southern part. Southern part has more population compared to the northern part, where the last center is opened. An important finding is that the determination of the location may not strongly depend on the local increase within the country. The sensitivity of the results to the distributional differences must be examined in more detail. Let's summarize our findings. We think that electric vehicle batteries should become part of a circular economy. Therefore, designing a good recollection process is crucial. In this paper, we present a tool to determine locations of recollection centers. The tool takes into account total and local growth of the vehicle market. We plan to update the tool as new information becomes available. Possible extensions are to use capacity information of recollection centers and try different battery lifetime distributions. New models can be formed that will extend existing recollection infrastructure. Finally, multi-objective models with several conflicting objectives can be used to analyze trade-offs. Here are the references of the presentation. And this is the end of my talk. Please email your questions and comments. Thank you for your attention.